Hello everyone. Today I'll be discussing three important methods from Calc 2 that are used to find the volume of three-dimensional solids. These methods are called the washer method, shell method, and cross-section method. While all three methods are used to find the volume, they approach the problem in different ways. The washer, shell method, and cross-section method involve revolving a two-dimensional region around an axis to create a three-dimensional solid. Throughout this presentation, I will explain each method represented geometrically and how the formulas are developed and when each method should be used. Let's begin with the washer method. Let's begin with the washer method. The washer method is used when a two-dimensional region is revolved on an axis and the resulting solid contains a hole in the middle. To understand why it's called a washer method, think about a washer used with a bolt. It looks like a circle with a hole cut out the center. When we rotate the region around an axis, each thin slice creates one of these washers. These slices are always perpendicular to the axis of rotation. Each washer has an outer radius and an inner radius. The outer radius, which we call capital R, is the distance from the axis of rotation to the curve that is furthest away. The inner radius, which we call lowercase r, is the distance from the axis to the curve that is closer. The small thickness of each washer is represented by dx or dy. By adding together the volumes of infinitely many washers, integration allows us to find the total volume of these solids. This image shows an example of the washer method. The red parabola represents the inner radius, while the blue line represents the outer radius. The green line shows one of the bounds where the two functions intersect. The entire shaded region, that should be shown right here, is the region being revolved around the x-axis. If you imagine taking one of the very thin vertical slices and rotating around the x-axis, it creates a washer shaped like a ring. Distance from the x-axis to the blue line becomes the outer radius. The distance from the x-axis to the red parabola becomes the inner radius. The volume is then found by subtracting the area of the smaller circle from the area of the larger circle and integrating across the interval. The equation v equals pi from the integral of a to b of big R x with x squared minus little r x squared dx. This is the way we find the volume. The reason we square the radii is because the area of the circle is equal to pi times radius squared. Since a washer is simply a large circle with a smaller circle removed, we subtract the smaller area from the larger area. The expression big R squared minus smaller r squared represents the area of one washer. Multiplying by pi gives us the actual area. Finally, integrating from a to b adds together all of the washers to find the total volume. The most important thing to remember is that the radii are always measured from the axis of rotation, which then can be shown in our function. We then have pi from 0 to 3 of the 3x squared minus x squared squared. We then square the functions. We then have pi from 0 to 3 of 9x squared minus x to the fourth dx, and then after we integrate it, we then are left with pi times 9x cubed divided by 3 minus x to the fifth divided by 5 from our bounds from 0 to 3. We then plug in our bounds, which leaves us with pi times everything inside parentheses of 9 over 3 times 3 cubed minus 1/5 and then 3 to the fifth minus 9, 3, which can all be shown in the example below, which then ends up being 162 pi over 5. Now we have shell method. The shell method approaches volume a little differently. Instead of creating washers, we create thin cylindrical shells. To visualize this, imagine taking a thin rectangular strip and rotating it around an axis. Rather than becoming a disc, it wraps around the axis and forms a hollow cylinder. These cylinders are called shells. In the shell method, our slices are parallel to the axis of rotation, which can be shown here in the blue rectangle. Each shell has three important parts: a radius, a height, and a thickness. The radius is the distance from the axis of rotation to the shell. The height is the vertical distance determined by the function, and the thickness is represented by dx or dy. So this is the application of shell method. This method shows how the shell method works. This function shown right here, f of x equals 2x squared minus x to the third, is being revolved around the y-axis in our example. And then, like I said earlier, the blue rectangle shows one of our thin slices, and you can visualize the orange circle around being our cylindrical shell. Notice that the rectangle is parallel to the axis of rotation, which is the y-axis. When this rectangle rotates around the y-axis, it forms that cylindrical shell. The radius of the shell is the distance from the y-axis to the rectangle. The height is determined by the value of the function at that point. The width of the rectangle becomes the shell's thickness. By adding together the volume of all these shells, we can determine the volume of the entire solid. We then use the formula v equals 2 pi from the integral of a to b with our radius times our height times dx for our thickness. The reason this formula contains 2 pi is because the circumference of a circle is equal to 2 pi r. Every shell can be thought of as the circumference multiplied by height and thickness. In other words, circumference times height times thickness. The radius tells us how far the shell is from the axis. The height comes from the function. Then the integral then adds together all of the shells to find the total volume. This method is often easier than the washer method when revolving around the y-axis because it avoids solving for x. But for our function, we then had our x, which is our radius, which is shown in the image, and then our 2x squared minus x to the third. We then just multiply x in, and then we are left with 2x cubed minus x to the fourth. So then we have 2 pi times everything in parentheses of 2/4 x to the fourth minus x to the fifth divided by 5 from 0 to 2. We then plug in 0 to 2, and then once we evaluate that function, we then are left with 16 pi over 5, which is actually our total volume of the cylindrical shell shown in the image. So now we are on cross sections. The cross section method is a little different, but still very similar. This can involve more common shapes like squares, rectangles, triangles, semicircles, and disc. When we imagine slicing the solid into many thin pieces, each slice is known as an area and a very small thickness. The volume of one slice is equal to its area multiplied by its thickness. The total volume is found by integrating all of those slices. One of the most important concepts in cross-section problems is determining the length of the slice. For vertical slices, we use the top minus the bottom. For horizontal slices, we use the right minus left. Once the length is known, we use geometry to find the area of the shape. The figure shows a cross-section example shown below. We have the purple function of f of x, and the black parabola is g of x. Together they form the base of the region of the solid. Imagine taking the very thin slice of this region. The distance from the lower curve to the upper curve determine the size of this cross-section. If the cross-sections are squares, that distance becomes the side lengths. If the cross-section are semicircles, that distance becomes the diameter. If they're triangles, that distance represents the base of the side. But since we have a parabola in a straight line, ours basically just becomes another disk. And we are revolving on the x-axis. So the formula for our application of the cross-section, since ours is actually ended up being the disk method basically, we have the volume is equal to pi times the integral for our function at 0 to 1/2, but in reality it's a to b, of big Rx minus small r x squared. So for our application, we then have the pi times the integral from 0 to 1/2 of 4x squared minus 16x to the fourth. This is after they've already been squared, which is shown in the volume formula above. We then have pi times 4 over 3 times x cubed minus 16 over 5 x to the fifth, showing our bounds from 0 to 1/2. We then plug in our bounds of 0 and 1/2. We first then plug in 1/2 since it's our upper bound. We then do pi times the entire function, which is shown. We then simplify, which leaves us pi times 1/6 minus 1/10, which then allows us to get pi over 15, which is our volume for the cross section, shown right here in purple and black, which is our volume for our this method.